3. Related rates. I always start this section by just kind of drawing a picture of a balloon. Is that a balloon? Does that look like a balloon? Let me try it again. Yeah. Yeah, like a whoopee cushion. Yeah. I don't know, something like that. There you go. That's a little better. Kinda. Maybe it looks like a whoopee cushion because it's red. Let me switch to blue. There you go. Now it looks like a blue whoopee cushion. Let's say that we have like an air compressor that is airing this up at a constant rate. Okay, instead of like us trying to do it with our breath, which varies. Let's say you have air going in at a constant rate. What are some things regarding the balloon that are changing as it inflates? You don't have to raise your hand or your foot. Just shout it about. The size? Like how would we quantify the size? Like the girth? The volume. I'll use V for volume. Is whatting as it inflates? Increasing. So I'm going to use an up arrow for increasing. Good. As it inflates, the volume's increasing. What else? That's it? That's about it. Right? Surface area. Good. I'll call that SA. It's also increasing. I said girth. I might as well do that. The girth G is increasing. That would be kind of like this, the diameter, I guess, if you will, straight across the widest part. It's also increasing.
Wouldn't its mass be increasing?
Yeah.
Because
yeah, the mass increases for sure. Yep. The pressure inside is increasing. How about the opacity? Oh, that's decreasing. I wanted to get one in there that decreases. How about if it's a spherical balloon? It doesn't look like it, but what if we measure the radius of the sphere to be r? Would the radius be increasing? Yes, and then the diameter would also be increasing. So on and so forth. And we probably go on, but I think you see the point here. There are a lot of different quantities in a simple thing like this that are changing over time as it inflates at a constant rate. Now here's the thing. All of these rates of change are not happening independently of each other. In fact, they are all what? Changing at a rate that is related to each other. They're all related to each other in the same system. So in this section, that's what we're going to be looking at. We're going to be looking at, first of all, rate of change over time. So we're going to be differentiating with respect to time, which is the ultimate independent variable. And we're going to be looking at systems where more than one quantity is changing. And at any given moment in time, we could talk about how these quantities are changing. Now, because most of the equations that we're going to be talking about are not going to have t, the variable, in them, we're still going to be differentiating with respect to time. So we're going to have to do it implicitly. Okay? Now, one of the main things in this section is reading a verbal description of a situation and then assigning a mathematical value to it. So we're going to be labeling all of our rates of change, whether they're ones that were given to us or ones we're trying to find. We're going to label them d quantity dt. So like up here, the rate of change with volume with respect to time would be dv dt. We're going to use Leibniz notation. The rate of change of the surface area, we might call dA dt for rate of change of area. Girth, d girth dt, right? Or dg dt, so on and so forth. Those are all going to be how fast those things change with respect to time. So like volume might be measured in cubic inches per hour, right? Surface area might be in square feet per, minute or something like that. So time will be our independent variable. All right, so when you read a scenario, you're going to have to assign it a variable. And if it's a rate equation, you're going to have to interpret the English words into a mathematical word. So let's go ahead and just do this on example 1. All we're doing is we're reading it, and we're going to put it into a math sentence from an English sentence. So Mortimer is growing at a rate of 3 inches per year. Now, what does it mean for Mortimer to be growing? Is it his belly getting bigger, or is his mind expanding? Let's just say that his height. Let's just say he's getting taller. Okay? So let's just call his rate of change of height with respect to time dH dt. Okay? So let's choose a variable that's kind of meaningful. If his height is changing, with respect to time, let's call it dHdt. Now, if you look back at the end there, it says 3 inches per year. So we're going to call that 3, and if you want, you can put inches per year behind it. Now, here's the number one thing that's important. Based upon the verbal description, you're going to have to assign it a plus or minus value. Because remember when we did the Colt-Yam sentences, it was kind of the other way around. We started with the math equation, and then we had to decide if something was increasing or decreasing. In the English sentence, you're always going to be given the rate of change, in this case 3, as a scalar quantity. And you're going to have to assign it a vector quantity, whether it's plus or minus, depending on the word. So if he's growing, is his height increasing or decreasing? Increasing. So if it's increasing, you're just going to leave it. You don't even have to put a plus sign, but I'll put it there for now. Okay, so you're going to label dHdt as 3. Okay, it's that easy. Stock portfolio, losing 5 cents a day. It could be your Goop coin or whatever you called it. I don't know. Yeah, Deutschcoin. Oh, Deutschcoin. Yeah. So let's call it the stock portfolio. Let's call it, how about V for value? The value or the worth. You could use W. A lot of times you get to choose your own variables. I'll use W. How about that for value with a W? How about worth? There we go. So I'm going to call the rate of change of the worth dW dt. And then 5 cents per day, I'll just measure it in cents per day. And then what sign am I going to ascribe to it? Negative. Good. So my worth is decreasing because it says losing. So there you go. A lot of times students can pick up on that pretty easily, but in haste, you might, just because you see a 5 there, you don't assign it a negative value. And that's where it's costly. If you forget to assign it a positive value, you're going to be okay, right? But when something is decreasing, you don't call it a negative value, then it's going to mess your calculations up. Radius of a circle is getting larger, so let's call that R. So dr dt is what kind of 4? Positive or negative? Positive, larger. I'm not going to put the units anymore. Outside temperature is dropping, so let's call temperature big T. So dt d little t by 5, positive or negative? Negative, good. Temperature's dropping. So there's a lot of different words we can use that get the same message across, right? Increasing or decreasing, increasing or decreasing. But when we're explaining our results, we like to use the words increasing or decreasing, and we'll save like words like dropping or larger. We'll save that for the poets. Okay, so here's a nice little example, real basic example. The length of a rectangle is decreasing by 2 inches per second, and the width is increasing by 3 inches per second. All right, can you visualize that? We have a rectangle and it's changing. How dynamic, wow. Now this is calculus, so that's instantaneous rate of change. So you're always going to be referenced a moment in time. But the moment in time is not going to say when t equals. It does start usually with when. So when the length is 10 inches and the width is 6, you're going to be referenced a moment in time by a certain condition that usually deals with some type of quantity, okay? How fast is, at that moment, the perimeter in the area changing? All right, so imagine that you're buying tickets to this event, right? The rectangle's changing? Yeah, sign me up. How much? $10? I'm giving you 20. It's worth it to me. Just keep the change, right? Like an optimization problem, we're going to draw a picture. So I'm going to draw a picture of just a generic rectangle. And anything that's changing at any time during the problem, you want to label as a variable because it will vary, right? It varies from one instant to the next. So we're talking about length and width, so I'm just going to name that L and name that W. So that's kind of what the diagram does. It not only kind of sets you up, but it allows you to define your variables. All right, now let's go ahead and see what we got. The length of a rectangle is decreasing. So just like we did in the thing above, I'm going to call that dl dt. Oops, dl dt. And it's what type of 2? -2. Yeah, everything's going to be measured in inches and seconds. If you want to put inches per second there, that's not a bad thing. And the width is increasing, so dw dt is what type of 3? Positive 3. Good. So anytime you have a problem like this, you want to label your givens. Okay, and we've done that. We've labeled the rates. The next thing we read when we keep reading is when the length is. So this is what I always call the snapshot moment. Cameras used to make a sound when you took a picture, the shutter. Maybe some still do, but that's the snapshot, right? So that means when the length is 10 and when the width is 6. I like to always draw those in an old-fashioned ugly camera with a flash cube on top. There used to be flash cubes, and you could get 4 out of them. You plug them in the top, and you rotated it, and every time you took a picture, it would be like a tiny explosion. And it would light the people up. So all the pictures came out like this back in the day, like, oh, tiny explosion, right? And you got 4 flashes out of each cube because you'd pick it up, turn it, rotate it, set it back down. So that's what I draw. That's my flash cube up there. These are the numbers that are only good at that moment in time, okay? So you always want to identify the snapshot moment. Whether or not you want to put it in a camera or not, that's up to you. Now we keep reading. At that moment then, when that picture was taken, how fast is the perimeter changing? Okay, so let's go ahead and give ourselves a target. I want to know how fast the perimeter is changing. That means I want to know the rate of change of perimeter. What variable can we use for perimeter? P, right? P for perimeter. So dp dt is equal to question mark. That's your target. You want to know what that is? Okay, so here's what we do. I have dl dt, dw dt, and dp dt. I ultimately want to relate those rates to each other. But every single time, before we can relate rates to each other, we need to be able to relate the quantity to each other. So in this rectangle, how can I relate the perimeter P to either the length or the width or both? The perimeter is what? Yeah, 2L plus 2W, right? Twice the length plus twice the width. L plus W plus L plus W, 2L plus 2W, right? There it is. This would be similar to quote unquote now our position equation, quote unquote, right? It doesn't tell us anything about change. It's a stagnant quantity. If you know the length and the width, you can find the perimeter at that moment. If you know the perimeter and the length, you can find the width at that moment. But now that I've related the quantity to each other, I can relate their rates with respect to time by differentiating both sides with respect to t. Now in optimization, we needed to have our equation as a function of a single variable. So perimeter as a function of L, perimeter as a function of W. You don't need to do that for related rates, okay? If you can, you might want to, and I'll show you what that is on the cone problems later on. But right now, it's not a big deal. So let's just take the derivative implicitly with respect to time. And this is going to give us our quote-unquote velocity equation, or the rate of change equation. So what's the derivative of P with respect to T? Well, it's dP dt equals, what's the derivative of 2L? Well, it's 2 times the chain rule, dL dt, plus the derivative of 2W is 2 times the chain rule, dW dt. Now, back when we did implicit differentiation, everything that had an x did not get a dx dx because that was just 1. But every variable that was a y got a dy dx. In this case, if you don't have a t in your equation, every single one of your variables is going to get a d variable dt. Okay? So this now is our quote-unquote velocity equation. Or, as we're going to call it, it's our rate equation. And now, if dP dt is our target, that's what it is we're trying to find, I need to go through real quickly here and see if I have everything else I need to find that value. There's 2 other variables in this problem, dL dt and dW dt. Do I know what those are? Yes. Not only do I know what they are, but I've got them conveniently labeled over there with the correct SIGN sign. Notice there's no quantity of L or W in this, is there? So what that means is it doesn't matter what the current size is, as long as the length and width are changing at a constant rate, the perimeter will change at that same rate. So now that I've got everything, now we just plug in. Now we always want to reference the moment in time when we plug in, right? Anytime you switch from a variable equation to a value equation, you have to either do like f of 3 or the Leibniz bar, but we're not going to do that here. So we'll just reference either one of these snapshot moments. It doesn't matter which one. I like making my cursive L. So I'm going to say when L equals 10, colon, and now I plug everything in. I get dp dt, which is what I'm looking for, equals 2 times dl dt, which is negative 2, plus 2 times dw dt, which is 3. And on a free response, you could stop there if you put units. I'm going to keep going. That's negative 4 plus 6. That's 2. Now the units, notice Leibniz notation. If you're not sure what they're going to be, you can just look at it. It's going to be units of perimeter over units in time. So perimeter is measured in the same units as length, so that's going to be inches per second. And there it is. Okay, now you might be asked to write a sentence explaining the meaning of your answer. Okay, and so if we did, I'm going to come up here with a different flavor. This goes back to the cold yam sentence now. When W equals 6 inches. Again, all you have to do is reference one of them. I picked W this time. But you do want to put units. At that moment in time, when the width is 6 inches, comma, the perimeter, or the rectangle's perimeter, if you just like writing more words, is whatting? Increasing. These are rates, so you either say increasing or decreasing, is increasing by 2 inches per second. All right. Remember, you have to answer it in, whoa. You have to answer it in units of, there you go. You got to answer it in units of perimeter, which is inches, and then per second. Okay, that's good to know. So one's getting smaller and the other's getting bigger, but at that moment, at that particular moment, the perimeter is still getting bigger. Okay. So it's like someone took a snapshot, like the event was going on, and we literally took a picture with our camera, and then after that, the moment was gone again, but we caught it for posterity. We're able to answer this question now, and we can answer the next one as well, right? Which is how fast at that same moment is the area changing. Well, that's part B. So very similarly here, we'll give ourselves a target. Area is A, I'll call it A. So I'm going to let dA dt equal my target. I want to know how fast the area is changing with respect to time. Now I have 3 rates of change. So I ultimately want to relate those rates to each other, but before I can relate the rates to each other, I got to relate the quantities to each other. So how in a rectangle can I relate the area to either the length, the width, or the perimeter, or any combination of those? Length times width, right. That's the easiest way. So again, this is a function of 2 variables. It doesn't matter. As long as we have all of our information after we take the derivative, we'll be able to plug everything in. So there's your quote-unquote position equation. Now I'm going to take the derivative with respect to t, and again, we show it like that with the verb ddt, and the left side becomes dA dt, and now I have to use the product rule on the right-hand side because I have 2 variable factors. So the derivative of L with respect to t is dL dt times W plus L times dW dt. And there's your rate equation. That's what we were after. Now I have 4 unknowns on the right-hand side. So if dA dt is my target, I better know all 4 of those quantities at that moment. Do I know dL dt and dW dt still? Yes. Now I didn't need the W and L from the previous one, but do I know what W and L are at this moment? Yeah, they're 10 and 6. So now those are meaningful. So I'll say when L equals 10, we get the rate of change in the area with respect to time is -2 times 6 plus L, which is 10, times 3, which comes out to be 30 minus 12, which is 18. And then the units would be units of area per units of time. So that should be inches squared or square inches per second. So that's your numeric answer. Your numeric answer is a rate that's either going to be a positive number or a negative number. When you write the sentence, as before, you interpret the sign as increasing or decreasing, and then you always use the magnitude, okay? So let's just say the sentence, I won't write it. At that same moment, right, when L equals 10, the area of the rectangle is increasing by 18 square inches each second or per second. How exciting. And that right there contains pretty much the entire essence of any related rate problem. Fantastic. Exciting. All right, questions on that? We'll go through several more, of course. By doing that, you'll get the sequence down. Because this is how you're going to be real successful. All right, example 3 is kind of the same, but it's a triangle instead of a rectangle. So I'm just going to kind of skip that and go to a more interesting version. You can read all that if you want. Just remember at the end you smile if you're not already smiling all the way through. All right, let's go down to example 4. Oil tanks do what an oil tank does, right? What are oil tankers designed to do? Not transport oil from one place to the next on the seas. They're designed to spill, right? Yeah, they're designed to spill. Not really, but they all invariably do. When it happened several years ago, that was the BP well, but the last one that I can remember that was really big was the Exxon Valdez. Got a hole in the side of it, and it was just spewing into the water there. So anyway, I'm sitting now. Let's go ahead and read on, right? An oil tank spills oil that spreads in a circular pattern. So this is onto the water. The pattern's radius R increases at a rate of 50 feet per minute on the surface of the water. How fast are both the circumference and the area of the spill increasing when the radius of the spill is 20 feet? Okay? And then there's a follow-up. So, drawing a picture here. Well, I guess I'll draw a picture of an oil spill, kind of at an angle here, so it's going to look like that, and then maybe like that, kind of concentric circles, but viewed from the side, all right? So here would be the center of the spill, and then I'm just going to call that the radius R as it emanates out. All right, and then if you want to really make it kind of nice, you could shade it if you want. So on and so forth. It's kind of fun. You get to draw pictures. And then you could draw like a fish that's trapped in there, right? Oh no, fish. That's a bad fish. There you go. Or a duck, whatever. So there's the circle, all right? An oil tank spills, blah, 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 whose radius R, so I called it R, increases at 50 feet per minute. So that's d what dt? If the radius R is increasing, yeah, so it's dr dt. And if it's increasing, of course, then it's positive. And I'll go ahead and put feet per minute here because just writing it down, that's me consciously thinking about what the units are. I'm talking about feet and I'm talking about time in minutes. And by the way, you know it's dt in this case. That comes up later on. Like, how do we know it's a related rate problem with respect to time? It's because it's with respect to time there, feet per minute, not feet per foot or something like that. Okay, so there's that rate labeled. How fast is the circumference changing? Let's do that first. I'll call it part A. So what letter can we use for circumference? C. So dc dt is equal to, it's my target. So in this part, I want to relate those two rates to each other, but before I do that, I got to relate their quantities. So in a cycle, how can I relate the circumference to the radius?
2 pi r.
Yeah, C equals 2 pi r. So there's your quote-unquote position equation. It's a stagnant quantity. I want the rate of change, so I'm going to take the derivative now of both sides with respect to t, and we get dc dt equals, the derivative of 2 pi r is just 2 pi, times the chain rule, dr dt. And there's your quote-unquote velocity equation, or your rate equation. Now, notice again that this one is not a function of the current size. I didn't do that yet, right? Did it say that? When the radius of the spill is 20 feet. So if I hadn't done it yet, I would say when r equals 20 feet, and I would put that in the camera. There's my snapshot moment. All right, well, in my rate of change of circumference, I don't even need the current size of the radius. It's only a function of how fast it's changing. But when we plug in, we're still going to reference that moment in time. So now we'll say when r equals 20, dc dt equals 2 times pi times positive 50, which is 100 pi, and then the units would be feet per minute. Okay, so the circumference of the surface oil spill is increasing by 100 pi feet every minute. The second part, how fast is the area, right? The area, as it says, and the area. Yeah, so this would be on top of the water, the surface area. So that's a very similar thing. I need to give myself a target. That's dA dt equals question mark. So now I need to be able to first relate the quantity area to either the circumference now or the radius. Which one's easier? The area is what of a circle? Pi r squared, yeah. There's a lot of geometric formulas that come out of here that we'll have to review and then y'all have to rememorize. So again, that's your quote-unquote position equation. Now we'll take the derivative with respect to time, and you get dA dt equals 2 pi r, which is the circumference, times the chain rule, dr dt. Don't forget, every variable will get a variable dt. And notice that does have an r in it. So now we'll plug in when r equals 20, colon, dA dt is 2 pi times 20 times 50. So that comes out to 10, 20, 2,000 pi square feet per minute, feet squared per minute. So again, that's the numeric answer. So at that same moment in time, like someone was out there in a rowboat and they took a picture when the radius was 20, and instead of trying to like help the animals or stop the oil spill, they're doing math, right? Did y'all know, like when the BP oil spill happened, I don't even know if y'all are, how old y'all were when that happened, but Kevin Costner, invented a surface skimmer, oil skimmer, to go clean the water, and he not only saved a lot of ocean marine life, but he made more money. Yeah, it takes money to make money. Kevin Costner invented a water skimmer that they used. It's pretty incredible. Pretty incredible guy. Okay, now follow up. Watch this. If the depth of the oil spill, and I always got someone back in there that says oil floats, it doesn't sink. Yes, it does. It does. Under its own weight, it will certainly sink. Right? It doesn't build up like a mountain above the water. Under its own weight, it gets pressed down below the surface. And that's where it really does the most damage to the things that live under there. So just imagine it continues spilling out on here, and as it gets bigger, underneath the water, like here's the surface of the water, underneath the water, it's kind of like pressing down on itself. And you got little fish in there that are trapped, right? Okay, so if you take straight down, this is what the depth would be. We'll call it D, because that's what it says. Now notice we're given the depth as a function of the radius. I don't know what it looks like under there, but they're telling me the depth at any distance r out from the center is given by 2r squared plus 1. How fast is the volume then of the oil spill changing at the same moment? Well, here's the deal, and this kind of goes back to like rectangular or geometric prisms. If you know the area of the surface, like let's look like we did with the soda can. If we knew the area of the surface, all we had to do to get the volume of the can was multiply by the depth or the height, right? It's the same thing here. If you know two of the dimensions, which we do on the top, the area is a two-dimensional quantity, then all you have to do to get the third dimension is multiply by that third dimension. So I'm going to come up here, part C. I want to know how fast the volume is changing, so dV dt is equal to question mark. So I want to be able to relate the volume to my radius. So the volume is going to be the area of the surface that we've already done, pi r squared, times the third dimension, which is d, which is 2r squared plus 1. Okay, so this is a two-dimensional quantity times the third dimension, and that gives you 3 dimensions, volume. That's all you have to do. Now I'm going to need the derivative of that, so do you want to do the power rule or product rule, or you want to distribute first? Distribute? Yeah. I'd probably, yeah. I'm all board for that. So we get 2 times pi times r to the 4th plus pi r squared. All right, now I'll take the derivative with respect to t. So dv dt is 4 times 2, that's 8 pi r cubed times dr dt plus 2 pi r dr dt. All right, there's your rate equation. It's your velocity equation, essentially. All right, and now we'll plug in. When r is 20, when r equals 20, we get dv dt equals 8 pi times 20 cubed times dr dt, which is 50, plus 2 pi r dr dt, which didn't we just calculate that down below to be 2,000 pi? So you can either put 2 pi times 20 times 50 again. I'm just going to bring 2,000 pi in there. And you could simplify that if you want to. I'm just going to stop there. What would the units be if I did stop there? Volume over time. So it should be cubic feet per, hopefully per year. Oh no, per minute. That's dire. Where's Kevin Costner when you need him? John Dutton?
No, Don Dish Soap.
Oh, Don Dish Soap. Oh, yeah. Kevin Costner does play John Dutton on the Yellowstone series. I think they have Don Dish Soap in the kitchen there on the ranch. Yeah, Don. There we go. All right, so that one was mildly more interesting, right? Got the hang of it? All right, this next one is like one of my favorite problems that we ever do. It's just so bizarre. I mean, look at the picture. Like, what the heck's going on there? You got a ladder leaning up against the wall. A 10-foot ladder, to be specific, is leaning up against the vertical wall. The lower end of the ladder is being pulled away from the wall at a rate of 2 feet per second. Any guesses on who's responsible for pulling the base of the ladder away from the wall? Looks like it's probably Dennis the Menace there, right? Now, what the heck is his buddy doing up there? First of all, he's staring at a wall.
He's watching the paint dry.
Maybe so. I don't think he's wearing those cool looking sunglasses. I think that's his actual eyes because he must be on something.
I think he's probably huffing the paint off.
He must be, right? Huffing the paint. Now, look at him. He's like doing toe raises on the second to top rung of this ladder. And look at his little calves. I mean, how is he even pulling? Whoa. How is he even pulling that off? He doesn't have like large calves, right? So the whole problem is just like bizarre. But anyway, it is what it is. The ladder is 10 feet. It's a fixed length ladder, which means as it slides down the wall, the length of the ladder does not change. That's going to be important. We can actually use their letters. If we let y equal at any given moment the height along the wall, and we let x along the floor be the distance from the base of the wall, we have two unknowns that change. X and y both change, but 10 is a constant, okay? It's being pulled away at 2 feet per second. When the lower end of the ladder is 6 feet away from the wall. So there's your snapshot moment. When? What variable is that? When what is 6? X or y? X, right? It says when the base of the ladder. So I'm going to draw my camera. When X is 6, at that instant, how fast is the ladder sliding down the wall? Okay, so here's part A. Give ourselves a target. The ladder sliding down the wall is a direct change in which of these variables? Y, right? The rate at which Y changes gives you the speed that it's sliding down the wall. So I'm going to call that, it already gave me the variables. If they hadn't, I would have called it something, probably X and Y anyway. So dy dx is now my target. And what else do I need to do? I need to finish labeling what I was given. It's being pulled away from the wall at the base at a rate of 2 feet per second. That's a direct change in which variable, X or Y? X, right? It's being pulled away at the base. So that's going to be dx dt. And is that going to be a positive or a negative number? As you take the ladder and pull it this way, is that distance increasing or decreasing? Increasing. So that's going to be a positive number. It's positive 6, and it's going to be feet per second. So that's about all I can do right now. Do I need to call the ladder length L for a variable L? No. If it doesn't change throughout the life of the problem, if it's a constant throughout, you don't need to call it a variable because it doesn't vary. But anything that does vary, even if you're given the snapshot moment, like you can't just call the base 6 right to begin with because it changes. It's only when someone took a picture that it happened to be 6 at that moment. Okay, so I need to be able to relate those two rates to each other, dx dt and dy dt. But as always is the case, before I can relate the rates, I need to relate the quantities. So in this right triangle, how can I relate x to y? Pythagorean theorem, yeah. So x squared plus y squared equals not L squared, but 10 squared, because 10 doesn't change. That's your quote-unquote position. It's your position because if you know x, you can find y, and if you know y, you can find x. All right, so now let's go ahead and take the derivative with respect to time. That's going to be 2 times x times the chain rule dx dt plus 2 times y times the chain rule dy dt. And then on the right-hand side, the derivative of 10 squared is 0, right? All right, so notice there's 4 variables in here. I can simplify, though. See that? I can divide everything through by a 2. And I would recommend doing that. Simplify early and often. It just makes your number smaller when you plug in. But now I need to know all 4 of those. So this is where you go through and you see if you have them. If not, then before you plug in, you want to go out and gather the rest of your ingredients that you need to make it happen. dy dt is what we're looking for. And for the first time, our derivative equation, the rate equation, is not solved explicitly for that variable. That's okay. I wouldn't even bother solving for it first and then plugging in. I would plug in and then solve. Okay, so if that's the only one I'm allowed not to know because I need to find that or I'm solving for it, I need to know the other three. Do I know x at the moment? At the moment, it's 6, right? So I know that. Do I know dx dt at the moment? Yes, I labeled that as positive 6. Do I know y at the moment? I do not. Bummer. I guess I'm done for, huh? No. All you got to do is use the position equation, right? When x equals 6, we get 6 squared plus y squared equals 10 squared. Now, you can either finish doing this. Y squared is 100 minus 36, which is 64. When I consider plus or minus, I only want the positive here because it's the length. Or you could have recognized it as a 3, 4, 5 right triangle that is magnified by a factor of 2. Either way, now I'm going to add that to my camera because it's still part of that same snapshot moment. Okay. All right, so I went out and gathered my ingredients. Now I can go ahead and plug in. When x equals 6 colon, I get 6 times dx dt. I'm sorry. Look, I mislabeled something. I just realized I have too many 6s, right? I labeled dx dt as 6. What is dx dt? 2. Yeah, y'all knew that. Y'all were just waiting for me to catch it. Thank you. 2. Yeah. So I got 6 times 2. It is positive. So 6 times 2 plus the y value, which we just found to be 8 times dy dt equals 0. And now I just need to solve for dy dt. So 8 dy dt equals negative 12. And if you divide through and solve for dy dt, you get negative 12/8, which simplifies down to negative 3/2. And if that's my final numeric answer, I better put units on it. So I'm going to come back up here again and see what they were. We're talking about feet and seconds, feet and seconds. So that's going to be units of y, which is feet, and seconds. Now, let's write the sentence that goes along with this, okay? When x equals 6 feet, or when the base of the ladder is 6 feet from the wall, that's a lot of writing. When x equals 6 feet, comma, the ladder is, I can either say sliding down the wall at positive 3/2 feet, or no, I could just say feet per second, sorry, because that's talking about the speed, feet per second, or I might be asked to talk about it in terms of the position. I could say when L equals 6 feet, the y is decreasing by 3/2 feet each second. We talked about that back in the day when you have to read carefully. Are you talking about how fast something's changing or how fast a quantity is changing? In this case, it did say how fast is the ladder sliding down the wall. So I would actually just stick with this right here. But when I say the word sliding down, that interpreted the negative sign. Okay. Okay. Now, is that a constant rate? If it says it's being pulled away at a rate of 2 feet per second, you could assume that that's a constant rate. Otherwise, it would have a variable in it, like it's being pulled away at a rate of 2x feet per second or something like that. All right. So is it reasonable to think that if it's being pulled away from the wall at the bottom at a constant rate, that it's sliding down the wall at a constant rate? Maybe. You can easily tell by looking at your equation. The rate of change down the wall is not just a function of dx dt, which is a constant. It's actually a function of that as well as 2 other variable quantities, isn't it? So is dy dt a constant? Or does it depend on x and y, which vary? Okay, this is actually not a constant rate. So here's how you can easily kind of imagine it. Imagine that one arm of mine is the wall. If you pull your elbow away from one arm at a constant rate, what's happening to essentially, that's the fulcrum of a lever. What's happening to that fulcrum? It's moving further and further back, right? And so the tip of the ladder is actually going to be accelerating towards the floor. Pull it back at a constant rate, and now because the hypotenuse is essentially longer, it's got more distance to cover in the same amount of time. So the bottom line is this guy with these puny ankles, when that thing does hit the floor, they're going to snap, right? But he shouldn't be up there to begin with. Okay, so it's not sliding down at a constant rate, even though it's being pulled away at a constant rate. Very important. All right, what else can we talk about in this wildly amusing scenario? At that same moment in time, how fast is the angle between the ground and the ladder changing? All right, so let's come back over here. And the angle between the ladder and the ground. So that's this angle here. What do you want to call it? I like theta. Call it whatever you want. So on part B here, I'm looking for d theta dt. That's my target. So now in this scenario, before I can relate the rates to each other, and by the way, I can now relate d theta dt to either dx dt or dy dt or both. I need to relate the quantities. So in a right triangle, how do I relate theta to the side lengths? So, right? Trigonometry. I would stay away from secant, cosecant, and cotangent. So I have three different sides. Which two sides does it make the most sense to get involved? X, Y, or 10? Two of those three. Which two?
R and X.
Yes. Why the hypotenuse?
Because there is a defined.
Constant, right? Is that what you mean? Yeah, it's a constant. So if you can eliminate a variable in your equation, by all means do so. Okay? And then why would we maybe choose to use X over Y? dx dt and x were both what? Given to us, weren't they? We just calculated y and dy dt. What if we made a careless mistake? Now we're using incorrect values for subsequent calculations, which if used correctly, we might still get full credit, but in the real world, not the best practice. Okay? So I would get x and 10 involved. So x is going to be the adjacent side, and then 10 is going to be the hypotenuse. So which trig function uses a and h? Cosine, right? Because it's TOA. So cosine of theta is the adjacent side x over 10. There's your quote-unquote position equation. Now you do have options at this point. We can actually solve this for theta easily by taking the inverse cosine of both sides. Okay, and we know how to take the derivative of our cosine, but we don't really need to do that. Okay, maybe I'll multiply both sides by 10 actually and get 10 x equals 10 cosine of theta. I think it's a little bit easier just to leave it in terms of cosine because the derivative is a lot faster. All right, so there's another version of the position equation. Now we'll take the derivative with respect to t. So d dt is dx dt equals the derivative of 10 cosine of blob is going to be negative 10 sine of the blob times the chain rule d theta dt. Okay. There's your rate equation. I'm trying to find d theta dt, so I have to know everything else. Do I know dx dt at the moment? Yeah, that's still the given. Now, do I know theta at the moment? No, I could find theta, but you know what? I'm not really after theta so much as I'm after the sine ratio of theta. And at this moment, when x is 6 and y is 8, don't I know all three sides at that moment? So I know all 6 trig functions at that moment. So yeah, I could do it. So I think we'll just plug in now. So when x equals 6, we get dx dt, which was positive 2, equals negative 10 times the sine ratio times d theta dt. So remember, sine is so, we're not on the coordinate plane, that's why I'm using SOHCAHTOA. So that's going to be the opposite over the hypotenuse. So 8 over 10. 8 over 10. Now all we got to do is solve for d theta dt, and your 10s divide out. So if you divide through by negative 8, you get d theta dt equals 2 divided by negative 8, which is negative 1/4. And now we have to put units on it.
Radians per second.
Very good. Degrees don't just come out of nowhere. If you don't have degrees anywhere else, they're not just going to magically appear. This is radians or rads per second. Radians are unitless, remember. And the angle is decreasing at this moment. Angle is decreasing. Yeah, the angle is The angle should be decreasing throughout, shouldn't it? If you imagine it being flush up against the wall, the angle's like pi halves. And as you pull it away, the angle between the ladder and the ground is going from pi halves down to 0 when it hits. So yeah, that's a reasonable answer. So the sentence would be when x equals 6 feet, comma, the angle between the ground and the ladder, I'm not going to write that, the angle is decreasing by positive 1/4 radians per per second. Yay!
Can you put increasing by a negative?
Don't, no. After the AP exam, when you're at home with your parents, say, look what I did, Mom, Pop. They're like, oh. You live life on the edge.
Increasing by a negative.
Don't do that. Don't do that. Don't toy with fate.
Don't screw with the grader.
Right? You're trying to clearly communicate, not show off how much of a jerk you are. Right? Okay. Any comments or questions on that? That's got to be about all we can talk about in this scenario. But wait, there's more. No. C. How fast is the area of the triangle formed by the ladder and the two walls changing? I was hoping they were going to ask me about the area of this triangle. Now, let's think about that for a second. If the base of the ladder were flush up against the wall, there is no area, right? Because it's 0. As I start pulling it away, I actually create a triangle, so the area is increasing. But then at a certain point, the triangle starts collapsing back down to the floor, so it ends up at 0 again. Where do you think the area is at a max when the angle is what? Because it goes from 0 to a maximum and then back down to 0.
I would say 45 degrees.
45 is a really,
Or pi-4.
yeah, pi force. That would be more of an optimization question, right? There have been related rate questions that are thrown into an optimization type scenario. And you're right, it is a 45 degree. But right now we're just talking about the area of the triangle. So let's go ahead and give ourselves a target. We'll call this part C. We're looking for, I'll call area A. d A dt is our target. So before I can relate the rates, I need to relate the quantities. And we got lots of quantities now, so I can either relate the area of that triangle to either x, y, or theta. If it's a right triangle, can we use 1/2 base times height? Yeah, we can. So that's going to be the area is 1/2 the base, which is x, times the height is y. 1/2 base times height. Cool. So now we take the derivative with respect to time, and we get d A dt, and now it's going to be another product rule. So we get 1/2 dx dt times y plus 1/2 x times dy dt. Now, I do want to point out, notice we can put y in terms of x or vice versa. If we look at the Pythagorean theorem, x squared plus y squared equals 10 squared, I could solve that for y and get the positive square root of 100 minus x squared and get my formula in terms of a single variable. But I don't think that's worth it because it's going to make the derivative a lot uglier. And if you look at the derivative we have, as long as we can find dx dt, dy dt, and x and y at the moment, we might as well just go with that route. And we do know all four of those quantities. So there's really not a benefit to putting it entirely in terms of x at this case, unless you really just like working with radicals and chain rules. So I do know all of these quantities. I have found them either in previous parts or I was given. So now we'll say when x equals 6, we get dA dt is 1/2 times dx dt, which is 2, times y at the moment, which is 8, plus 1/2 times x at the moment, which is 6, times now dy dt. Good thing we did part A first, right? I can import dy dt, which we found in part A right there, and remember it was -3/2. Now, without simplifying that, do you think at this moment in time, when x is 6 and y is 8, if 45 is the optimal area, should the area still be increasing or decreasing at this moment? It's being pulled away from the base. Right now it's 6 and it's 8 up top, so they're not quite equalized yet, right? So if we're right, the area should still be increasing, right? We're not quite at the 45. So this should be a positive quantity, even though it has a negative term. Let's see. We're going to get 8, and then let's see what this comes out to. 3 minus 9/2. I think that's right. So 16 minus 9, 7/2, or 3.5. Positive 3.5. And then area per time. Area per time. So if we're measuring in feet per seconds, this would be square feet per second. And it is a positive number. So the area is still increasing at that moment by 3.5 square feet each second, right? All right, and then the last one here, we've already kind of talked about this, part D. What's the acceleration of the ladder down the wall? I've already kind of told you that it is accelerating down the wall. We want to quantify that. So, what are we looking for then? What is this, A, B, C, D? F double prime. Well, if dy dt was the velocity down the wall, the derivative of that with respect to time would be d squared y over dt squared, right? Now, in Leibniz form, that's the acceleration down the wall. So we are looking for the second derivative, but we're looking for the second derivative of y with respect to time. So I need to relate the quantities to each other first. Well, remember when we took derivatives earlier in the year in position? We had position, then velocity, and then to get the acceleration, we just took the derivative of the velocity. We could still do that. Let's come back up here to part A, and we'll look at this version right here. That was the simplified one before we plugged in. So I'll copy that, bring it down here, and get rid of those stray marks. Okay. Now all I got to do is take the derivative of that again. But as you also remember in implicit differentiation, when we took second derivatives, it was always a lot easier to find the second derivative if we solved the first derivative first. We're not always able to solve for the single variable, but once we solve for dy dx, it was easier to find the second derivative. So let's solve for dy dt first, okay? So I get y dy dt equals negative x dx dt, and then I get dy dt equals negative x dx dt all over y. That looks kind of gross. But is there anything that we can plug in before we take the derivative, or no?
Or X is the Y value?
Well, if I plugged x and y in right now, it's only equal to 6 and 8 respectively at that moment in time, right? So we can't plug in and then take the derivative, otherwise we're going to get 0. The only thing that we can plug in before we take the derivative is anything that does not change throughout the life of the problem. That is anything that is truly a constant throughout the entire problem. X varies throughout the problem, and so does y. But what about the x dt? It's a constant, yeah. So that's one of those reasons why we didn't need to label the length of the ladder L. We knew in the beginning it was a constant. Okay, so I would plug that in first. So you just got to be a little bit astute, okay? And making you aware of it now helps you realize it later. So dx dt, remember, was positive 2. So this just turns into negative 2x over y. Now, we could have done that in the very beginning on part A before we plugged in, and then we could have easily just plugged in a 6 for x and an 8 for y and gotten the same answer of negative 3/2. Okay, I just think if you're only using it once, it's easier to plug in and then solve. You're not working with so many variables that way. All right, so now let's take the derivative with respect to t, and we get the second derivative of y with respect to t squared is, and I'm going to do the Hody high rule on this side. I hope you are too. So O d high is negative 2 dx dt, Hody high, minus high d ho is dy dt, all over ho ho, which is y squared. Now, remember on part A, we said dy dt was negative 3/2. Is the speed of the ladder down the wall increasing or decreasing? The speed down the wall is increasing, right? It makes sense because, again, like I said, the lever's getting longer, and so I don't want to be that guy on the ladder when it hits. Think back to speed. It's a scalar quantity. Speed is only increasing when velocity and acceleration are the what? Same sign, when they're both working together. So if the velocity is negative, the acceleration has to end up being negative as well, right? So d squared y over dt squared should be less than 0 too. Just something to think about, just reviewing another topic. I could easily just plug in and found out that it was negative. All right, so now we're going to go back to the same moment in time when x is equal to 6. The acceleration of y with respect to t is, y at the moment was 8. Negative 2 is negative 2. dx dt is 2, right? This becomes plus 2 times x, which is 6, times dy dt, which from part A was negative 3/2, and then all over 8 squared. Let's just keep going here. That gives us negative 32. That's going to be minus 18 all over 64. So negative 50 64ths, which comes out to be negative 25 30-seconds. And what are the units here? Feet per second squared. Yeah. Let's go ahead and write the sentence. When x equals 6 feet, comma, the speed of the ladder down the wall, and we can answer it like that because speed is the scalar quantity of velocity. The speed of the ladder down the wall is increasing. Actually, let's do this. Instead of saying speed, let's make it more of a vector statement. Because we can say the speed of the ladder down the wall is increasing, but let's do the velocity of the ladder down the wall is now what, Tim? Decreasing. The speed down the wall is increasing, but the velocity down the wall is decreasing because acceleration is the rate of change of velocity. And if it itself is negative, velocity is decreasing. So again, you can answer it in a lot of different ways. The velocity of the ladder down the wall is decreasing by positive 25, 30 seconds, and then we answer it in velocity units, feet per second, PER seconds. So kind of fun problems. Goes back a little bit to the Harvard worksheet, the cold yam type problems, but they're really not that difficult. Once you get the hang of the setup is worth everything, right? If you don't scrimp on the foundation of a house, everything after that's going to go a lot more smoothly. Same thing here. If you go through and you clearly read and label quantities, identify your snapshot moment, give yourself the target, the rest of the problem is going to go pretty smoothly after that. Okay, so again, a great problem just because it's one crazy scenario, but we could talk about a lot of different things from it. As you've noticed so far, related rates is just so far a bunch of geometric quantities, whereas optimization was a little bit different. We kind of had to, some were geometric, like when you were inscribing cones and cylinders and spheres, but a lot of times it wasn't. All right, so good so far? All right. Hey, let's return to the original problem. A spherical balloon is being inflated at a constant rate of 5 cubic inches every minute. When the radius of the balloon is 4, how fast is the surface area changing? Oh, okay. Draw a picture. There's a sphere. There we go. There's the radius. It's being inflated. So what are we going to label 5 cubic inches per minute as? V, good. You get the hint from that, right? Cubic inches, that's a unit of volume. So we'll say dV dt is what type of 5? Positive or negative? Positive, yeah. If the balloon were deflating, it would be negative, but it's positive, okay. When the radius is 4, so the snapshot moment is when R is 4 inches. So how fast is the surface area changing? So I'm going to call that dA dt, that's my target. Now, this one's kind of interesting because I ultimately want to relate the area or the rate of change of area to the rate of change of volume, but I need to first relate their quantities. Is there a formula that y'all have memorized for the volume of a sphere in terms of its surface area? Ooh, no. But let's write down what we know. Let's just take some inventory over here. I do know the volume of a sphere in terms of the radius. What is it? Good, 4/3 pi r cubed. Memorize if you don't have that memorized already. That's the volume of a sphere. The surface area of a sphere, I'm going to call it SA for now. It's just the derivative of the volume with respect to r, not t. So it's 4 pi r squared. So because I have an r as the only variable in both of those, I can relate those to each other by way of r. Now you have two options. You can actually solve one of them for r and plug it into the other one, or you can just work with both quantities simultaneously. Y'all have really no idea which one's easier than the other. So maybe let's try both of them. It's only going to increase your level of understanding, and then you can draw your own conclusions. So I'm going to do part one. Let's work with both. I still think this might be a little bit easier. I'm going to take the derivative of both with respect to t. So I'm just going to kind of do it in rows here. d dt of v is going to give us dv dt equals 4 pi r squared times dr dt. Well, let's keep doing the same thing. We'll do the area now. The rate of change with the area with respect to time is 8 pi r times dr dt. And let's see. Now I can say dA dt, which is this one here. That's what I'm really after, right? I need to know dr dt at the moment, do I? No. But do I know the radius at the moment? Yes. So how can I find dr dt at that moment? Well, enter equation number 1. Okay, so when r equals 4, let's just plug it into the top one. We get dv dt, which we know is 5, to equal 4 times pi times 4 squared times dr dt. We can now solve that for dr dt. That's going to give us a 16 times 4, that's 64. So dr dt at that moment is going to be 5 divided by 64 pi. And now that I have dr dt at that moment, now I have all I need for the second one. So again, when r equals 4, I get dA dt equals 8 times pi times r, which is still 4, times dr dt, which is 5 over 64 pi. And that's a number. So if you wanted to stop there in a free response, units would be inches squared per minute. Let's keep going though. I think I want to simplify. So in the top here, I have a 32. 8 times 4 is 32 pi, which divides out with 64 pi. So I end up with just 5 in the top over, I'm left with the 2 in the bottom. And that's a lot prettier answer, inches squared per minute. So that wasn't too bad. You just work with both of them and it works itself out. You're just using one of them because you're given V, you got to go through the volume equation and it ultimately gives you dr dt, which you then can use to plug in the other. All right, the other option is to get A in terms of V. So what I'm going to do, since I want to ultimately solve for A, it's kind of nice if it's already solved for A if I want dA dt. So I'm just going to solve this one up here for R. So I'll come over here. If the volume is 4/3 pi r cubed, let me solve that for R. That's really the same as 4 pi over 3, just to take a step out of it. If I multiply both sides by the reciprocal, then I get 3v over 4 pi equaling r cubed. And instead of taking the cube root of both sides, because I don't like working with cube roots, especially when we're taking derivatives, let's just raise both sides to the 1/3 power. So I get r is equal to 3v over 4 pi to the 1/3 power. So the area, surface area, which is 4 pi r squared, is now 4 pi r squared. So that's going to be 4 pi r squared. Well, that's going to be 3v over 4 pi squared to the 1/3. Well, when I raise a power to a power, what do I do with those? I multiply, right? So I get 4 pi times, I'm going to call this 3 over 4 pi now, times v to the 2/3. In other words, I kicked the v out of the numerator because I want it to now look like a coefficient times v. Okay. Now, I don't think it's worth distributing the 2/3 to each factor and bringing the 4 pi and the 3 over 4 pi to the 2/3 together. I would just leave it like this. So now I'll take the derivative with respect to time, and I get dA dt equals, the 4 pi goes along for the ride, times, now the derivative of this, it's a chain rule. So it's 2/3 times blob to the -1/3, blob goes along for the ride, times the derivative of the blob, which is 3 over 4 pi, times dV dt. Yucky, yucky, gross, gross. Y'all want to finish this way?
No.
I don't either. It works, but I know dV dt, it's 5. But I don't even know the volume at that moment, do I? So I would have to come back over here and figure out what the volume is when the radius is 4. And I guarantee if you do all that, you'll end up with 5/2. So you could draw your own conclusion there, which version you like better. I think if you have to relate two quantities together that you don't really have a formula for in your head, but you can relate them both through a third-party variable, just do it the way we did on the first one. Just work both of them simultaneously and then use the given information to plug in what you know, and it'll work itself out. It'll give you the other quantity that you're still missing ultimately in that one you were looking for. I didn't have the RDT, but I was able to find it. Okay. All right. It's probably a good place to stop. We'll do example 7. Yeah, we'll finish next time because we got cones next time. Basically, cones, and more cones, and then a slightly different application on the ladder against the wall problem on example 7. So I'm going to create 5 questions in AP Classroom tonight that go through this part of related rates. So those will be due on Monday. I will be grading your tests also tonight and tomorrow, so I should have them in tomorrow by the end of the day. I apologize. I did A/Bs first and had to track down about 5 or 6 missing tests. I don't know how some people just can't figure out how to turn a test in on time. AP students, but not y'all. I got all y'all. So anyway, any questions at home? Any questions here? Devin, Gavin, Kaya, Mia, Zach, y'all can log off if you need to. Everyone else, we'll sit tight for just a smidgen longer. 10 more minutes. Yeah. By the time class ends, I should have AP Classroom done, hopefully. Adios.